Welcome back to the deep dive. Today, we're getting into some really cool physics. We've got these sources covering everything from, throwing a ball to how satellites actually stay up there, projectile motion, and satellites.
That's right. And our goal really is to bridge that gap. How does the simple act of tossing something connect to, well, keeping a space station in orbit or sending probes deep into space? We're going to try and break down Newton's laws and orbital mechanics in a way that, makes sense for you, the learner.
And what I love is how grounded this is right from the start. The sources aren't just equations. They mention real people working at places like JPL, the Jet Propulsion Laboratory.
Yeah, people applying this exact physics, designing things like parts of the landing system for the Curiosity rover on Mars. It's not just theory.
Exactly. It shows that this fundamental stuff, this atish haraketi, or projectile motion, as the source calls it, is what makes space exploration possible. Every single movement is calculated using these ideas.
Precisely. It governs the entire journey. So let's lay down the basics. Projectile motion. Fundamentally, it's about an object moving in a curved path, and the main force acting on it is just gravity.
Okay, so what's the first big concept we need to grasp?
The absolute key, the thing that unlocks it all, is understanding that the motion has two parts, horizontal and vertical. And crucially, they are independent. What happens horizontally doesn't affect what happens vertically, and vice versa.
The classic thought experiment, right? Firing a bullet horizontally and dropping one at the same instant.
Exactly that one. And ignoring air for a moment, they hit the ground simultaneously. The forward speed of the fired bullet has zero impact on how fast gravity pulls it down.
So the horizontal part of the velocity, dx, just stays constant, assuming no air drag, of course.
Correct. Nothing's pushing or pulling it sideways once it's launched. But the vertical velocity, V8, that's constantly changing.
Because of gravity, always pulling down.
Always pulling down. Constant downward acceleration slows it going up, speeds it up, coming down.
And that combination, steady forward motion, accelerating downward motion, that gives us the curve, the parabola.
Yep. Even in the simplest case, like rolling a ball off a table, it moves out steadily but falls faster and faster. Perfect parabola.
Okay, so let's angle that launch.
Yeah.
If you want maximum distance, throwing a ball, firing a cannon, whatever, what's the ideal angle?
In that perfect physics world, the vacuum, it's 45 degrees, bang on. The sources confirm this. It perfectly balances putting energy into height, which means more airtime, and putting energy into forward speed.
Right. And there's that neat little detail, too, in a vacuum. Angles that add up to 90, like 30 and 60 degrees, they give you the same range, just different heights and flight times.
That's the clean, theoretical model. But we don't live in a vacuum. What happens when reality kicks in with air resistance? Habiturency, as the source terms it.
Yeah, air resistance. The party pooper for perfect parabolas. It messes everything up.
It really does. And this is important for you listening. It doesn't just shorten the range and lower the peak height. It actually changes that optimal angle.
How?
Well, air resistance depends heavily on speed, right? And it's also denser lower down. Launching at 45 degrees gives you a high arc, meaning the object spends more time moving relatively slowly high up, but it fights more drag overall, especially at the start.
So you want to kind of cut through the thick lower air faster, minimize the time you're fighting the worst of the drag.
Exactly. So in the real world, hitting a golf ball, throwing a baseball, that optimal angle for maximum distance, it drops. It's usually closer to, say, 30 or 35 degrees, not 45.
Interesting. So you trade some potential flight time for less overall drag by keeping a lower trajectory with higher average speed.
Precisely. That shift from 45 to maybe 35 degrees is a direct consequence of factoring in the real world. Okay, so that's getting things across the ground. But how do we get something to, well, never land? How do we jump from throwing things to orbit?
This requires a shift in thinking, right? Moving beyond just a flat surface.
Totally. We need to think about the Earth itself curving away. This leads us straight to Newton's brilliant thought experiment.
The cannon on the mountaintop. Love this one.
Yeah, imagine a ridiculously high mountain above the atmosphere. Fire a cannonball horizontally. Too slow. It arcs down and hits the Earth.
Fire faster.
It goes further before hitting. But here's the magic. The Earth is round. Its surface curves downwards.
Right. So if you fire it fast enough.
Fast enough horizontally, yes. The cannonball is still falling due to gravity, always falling, but its horizontal speed is so great that the Earth's surface curves away beneath it at the exact same rate it falls.
So it falls, but it constantly misses the ground. It's falling around the Earth.
That's orbit. Perpetual falling, perpetual missing. It's not about overcoming gravity, it's about having enough sideways velocity to match the curve. So what speed do we need for that perfect circular orbit, just skimming the atmosphere?
It's got to be incredibly fast.
It is about 8 kilometers per second. That's roughly, what, 18,000 miles per hour? That specific speed gives you a stable circular path close to Earth.
Okay, 8 kilometers for a circle. But what if you go a bit faster than that, but not fast enough to just fly away completely?
Then you transition from a perfect circle to the more general orbital shape, an ellipse. Most orbits are actually elliptical. Circles are just a special case.
And ellipses bring in those terms, perigee and apogee.
Exactly. Perigee is the closest point in the orbit to Earth. Apogee is the farthest point. And the satellite's speed changes throughout this elliptical path. It's all about energy conservation.
Okay, so total energy, the kinetic energy from moving, plus the potential energy from height that has to stay constant.
That's the rule. So think about it. As the satellite climbs towards apogee, its farthest point, it's gaining altitude.
So its potential energy goes up.
Right. And since the total energy must stay the same, its kinetic energy must go down, which means...
It slows down, slowest speed at the farthest point.
Precisely. Then, as it swings back down towards perigee, it loses altitude, a potential energy drops.
So kinetic energy must increase. It speeds up, fastest at the closest point.
Yep. Gravity is essentially trading height for speed and back again, constantly.
But wait, if it's moving slowest way out at apogee, why doesn't gravity just sort of win then? Pull it back in.
Good question. Because even at its slowest, its horizontal velocity is still high enough, it's still moving fast enough sideways that the Earth continues to curve away beneath it. It's slow compared to its perigee speed, but still fast enough to stay in orbit. The balance holds.
Okay, that makes sense. It never quite slows down enough horizontally to fall straight down.
Correct.
Yeah.
Now, let's push it further. What if we want to leave orbit entirely, not just stay up, but break free? That brings us to escape velocity, kurtulma hızı.
The speed to say goodbye to Earth's gravity for good.
Essentially, yes. It's the minimum speed an object needs so that its total energy kinetic plus potential is 0 or positive. If it reaches that, gravity can slow it down, but never enough to actually stop it and pull it back. It will coast away forever.
So what's the magic number for Earth? How fast do we need to go?
For Earth, it's 11.2 kilometers per second. Notice that's significantly faster than the 8 kilometers needed just for orbit. You need that extra kick to overcome the gravitational binding energy completely.
11.2 kilometers. That's
Yeah.
really moving. How does that compare elsewhere? The sources had some great comparison data.
Yeah, the scale is amazing. Look at the moon. Small body, weak gravity. Its escape velocity is only 2.4 kilometers. Much easier to leave.
Makes sense. But then the giant planets.
Jupiter, the beast. Its escape velocity is a massive 59.5 kilometers, over 5 times Earth's. Imagine the fuel needed to launch something off Jupiter compared to Earth. It really puts the energy requirements into perspective.
And the sun, just out of curiosity.
The sun holds the whole system together. Its escape velocity is a staggering 618 kilometers. That's why everything orbits it.
Wow. Okay, and these aren't just numbers on a page. We actually use this, right, for deep space missions.
Absolutely. Probes like Pioneer 10 going to Jupiter or Cassini heading to Saturn, they had to achieve speeds greater than Earth's 11.2 kilometers escape velocity just to leave Earth's influence and begin their long journeys across the solar system.
So we've gone from the basics of throwing something, that independence of motion,
To the ideal 45-degree angle, in theory, the real-world angle with air drag, then the 8 kilometers needed for orbit.
and finally, the 11.2 kilometers to escape Earth entirely. It all connects.
It really does. These principles are literally how we navigate the cosmos. It's the physics that lets us plot trajectories across millions of kilometers.
You really should acknowledge the sources again here. This set of physics excerpts, credited to Fizik Öğretmeni Hashi Velitorun, does a fantastic job laying this out step by step. Really clear and insightful.
Agreed. A very solid foundation for understanding this complex topic.
Okay, let's wrap up with something to chew on. We saw Jupiter's huge escape velocity, nearly 60 kilometers, versus Earth's 11.2 kilometers. If we're thinking way ahead about future large-scale space infrastructure, maybe transport hubs, does that massive gravity well around Jupiter make it, or even its large moons, fundamentally impractical as major launch points? Should we prioritize building launch facilities on low-gravity bodies like the Moon or Mars, even if they're less central, just purely because the energy cost of the fuel cost of escaping is so much lower?
Sure.
How do you balance the sheer physics cost of gravity versus, say, strategic location of the solar system?
That's a fascinating trade-off. The energy difference is truly enormous, something for you all to think about until next time.